1. Calculate the pH values of a strong acid and base. 2. Relate the strength of weak acid and weak base to the respective dissociation constants K, A, and K, B.
Okay, now we move to the next part. Right? How we can determine acid and base as a strong one or a weak one. For a strong acid, acid is a completely dissociate in aqueous solution to produce a very high concentration of H3O+. It is essentially 100% dissociate or equivalent to alpha equal to 1. The degree of dissociation means 1. So, for both example HCl and HNO3 in water, they are completely dissociate. So, the symbol here is completely dissociate to form the H3O plus aqueous and the Cl minus. While a base completely dissociates in aqueous solution to produce a very high concentration of OH minus. It's also essentially 100% dissociate, or we can say the degree of dissociation is equal to 1. Example, the ammonia. The example of NaOH. NaOH is completely dissociate to form the Na plus aqueous and the OH minus. So, in here, we can say that the alpha is known as the degree of dissociation. Alpha means the concentration of either H3O plus or OH minus concentration over the initial concentration of acid and base. Alright, we move to the weak acid and weak base. If a strong acid is completely dissociate, while a weak one is partially dissociates in aqueous solution, it produces a low concentration of H3O+, which means the percentage dissociate is less than 100% or alpha is less than 1. Example, a weak acid of CH3COOH in water, it produces the CH3CO- ion and H3O+. Here we can see that the symbol that we use is partial arrow, reversible arrow. The weak base here shows that the partially dissociate in aqueous solution to produce a low concentration of OH minus, which means that the percentage of dissociation is less than 100% or alpha is less than 1. For example, the ammonia react with water to produce the ammonium ion of NH4 plus and the OH minus. So, both example of equations shows that reversible reaction take place to show that this is a weak acid and weak base. Alright, now we move to the pH measurement, the pH scale. How we are going to express the acidity or basicity for a solution. Acidity of the solution is determined by the pH scale, range from 0 until 6, while the alkaline or basicity of the solution is range from 8 until 14. Numbers of 7 in pH scale is referred for the neutral solution. In neutral solution, when pH equal to 7, the concentration of the positive of H3O plus is equal to the OH minus. For the acidic solution, what we can be determined is the pH value is less than 7, which means the H3O plus is greater than OH minus. For the basic solution, pH is greater than 7, which means the concentration of the OH minus ion is greater than H3O plus. So, from this statement, we can conclude that pH is measured on the concentration of the H plus or the H3O positive ions in a solution, while pOH is measured of the concentration of OH minus ion of a solution. pH is defined as a negative logarithm of the concentration of the hydrogen ion, as stated here, while the pOH is defined as a negative logarithm of the concentration of hydroxide ion, as is stated here. Right. About the water, the ionization of water. In water of H2O liquid compound, it is partially dissociate to form the H plus aqueous and the OH minus aqueous. Since it is partially dissociate, means that the degree of dissociation of water is extremely small. So the H2O concentration is assumed as a constant. So here we can write down the Kc times the H2O equal to H plus concentration ion times to the OH minus concentration ion. So when the concentration H plus minus ion times the concentration of OH minus ion divided by the concentration of H2O is formed a Kw. So Kw is known as a water ionization constant or ionic product of water. This Kw value will increase with temperature because the dissociation of water is an endothermic process. For example, for pure water at 25 degrees Celsius, the concentration of the H plus ion and concentration of OH minus ion are both is 1 exponential 10 to the power of negative 7 molarity. So, formula of Kw equal to concentration H plus times the concentration of OH minus ion. So, Kw, we add the value of 1 exponent negative 7 concentration. So we get the value of Kw is 1 exponential negative 14 molar square. So this is Kw value for pure water at 25 degrees Celsius. Right. The relationship between pH and pOH to Kw at 25 degrees Celsius. As we learned before, Kw value is 1 exponential negative 14. So from here, we can relate with concentration of the H3O positive ion and the OH minus ion. So how about take the negative logarithm at both sides? And what will happen? It finals to be concluded as a pH plus the pOH equal to the 414. Take note on this. Kw equal to concentration H3O positive ion times the concentration of the OH minus ion. Kw equal to 1 exponential negative 14 at 25 degrees Celsius, and pH is negative logarithm of concentration H3O positive ion, while pOH is negative logarithm of concentration OH negative ion. pH and pOH, the sum of pH and pOH equal to 14. So please bear in mind all these 5 important equations. For the weak acid, as we learned before, weak acid is partially ionized in aqueous solution. At the equilibrium, an aqueous solution of weak acid contains a mixture of non-ionized acid molecule and its conjugate base. In general equation like this, Ha is referred to the weak acid. When it react with water of H2O, it's going to form the A minus aqueous and H3O positive ion. The Ka value is concentration of the product of A minus ion times the concentration of the H3O positive ion divided by the concentration of the Ha, weak acid. So the percentage of acid dissociate here can be calculated by knowing the acid dissociate concentration divide with the acid initially times 100. So the percentage will show us how weak that acid was. Here, in this table, shows that the ionization constant of some weak acids and a weak bases in water at temperature of 25 degrees Celsius. As we can see here, the Ka value and the pKa value. So when the Ka be getting smaller, the pKa getting higher. Right? Also in Kb value, while the Kb value getting smaller, the pKb value getting higher. So the value of Ka indicates the degree of dissociation of weak acid in water. Means that the lower the Ka value, the weak will be the acid in the water. So the larger the Ka value, the stronger the acid. Means the more ions are present at equilibrium that relates to unionized molecule. If the Ka is greater than 1, it shows that the acid is completely ionized and that acid becoming a strong acid. So the percentage of ionization of weak acid will decreases as the molarity of the solution increase. So the graph show the percent ionized when the acid concentration increase. Here is a few example of an acid. The formic acid, acetic acid, and another such example of acid that having a different number of Ka value. The Ka become less from the HCOOH until the HCN. When the higher the Ka value, we can say that the stronger the acid. So in this order, we can arrange that increasing order of acid strength, the HCN is the weakest one, followed by the H2CO3, since HCN have a smallest number of Ka value, and the highest one shows by the HCOOH. Also in for weak base, it's a partially ionized in aqueous solution. At the equilibrium, the aqueous solution of weak base is contain a mixture of non-ionized base molecule and its conjugate acid. This is an example. A weak base of X in H2O is going to produce the HX positive aqueous and OH minus aqueous. From here, we can obtain the Kb value to show that the weak base HX positive ion times the OH negative ions and divide by the concentration of X to get the Kb value. So the percentage of base of dissociate can be arranged by base dissociate concentration divided by initial base concentration times the 100. Here is a few examples that relates on the base, such as C6H5NH2, NH3, C2H5NH2, that having their own Kb value. As we can conclude here, the higher the Kb value, the stronger the base compound. For example, here C2H5NH2 have the highest Kb value, while the C6H5NH2 having the smallest Kb value. So the decreasing order of basic strength shows here. Right, here the relative strength of conjugate acid and base pair for the acid and base. As we can see, a very weak basis is a negligible tendency to be protonated in aqueous solution. Such example from ClO4 minus, Cl minus, HSO4 minus, and O3 minus, because it comes from the strong acid, which is completely dissociate, 100% dissociate in aqueous solution, such as HClO4, HCl, H2SO4, HNO3. The moderate tendency to be protonated in aqueous solution because it is within the weak acid range, such as HSO4 minus until the HCO3 minus. And the weak, very weak acid to dissociate, such as NH3, OH minus, and H2, it shows that tendency to have a strong bases, 100% protonated in aqueous solutions. So the weaker the acid and will be the stronger in base. While stronger in acid, it shows the weaker in base. Alright, this is the relation between the acid dissociation constant of Ka and the base dissociation constant of Kb. Value of Ka or Kb can be used to distinguish in the relative acidity strength of weak acid and weak base. As we learned before, if the Ka value is higher, means that the pKa value is lower. If the Ka value is higher, means the concentration of the H positive ion is high. Thus, the pH value is lower, which means it is more acidic. Example, between these two acids, an acetic acid and formic acid. Acetic acid having a pK value of 4.74, while the formic acid have the pK value of 3.76. In the relative acidity tendency shows that the acetic acid is more acidic than the formic acid. So the pKa is negative log Ka. For the Kb value, increase shows that pKb is lower and the concentration of OH minus ion, hydroxide ion, is increased when the Kb value is higher. So the pH value is higher, which is mean that the solution is more basic. For example, C6H5NH2 aniline and the NH3 ammonia. Aniline have a pKb value of 9.37, while the ammonia have 4.74 the pKb value. So the NH3 is greater than C6H5NH2. So the pKb equal to negative log Kb. When we mix together between the K and Kb, here is the relationship that show between Ka and Kb. I use this example of NH4 positive and its pair of NH3. So we consider the acid-base conjugate pair of NH4 positive and NH3, the dissociation of both species in water. For example, NH4 positive ion, when it's dissociated in water to produce or to perform the NH3 aqueous and the H3O positive aqueous, the NH3 aqueous react with the H2O to form the NH4 positive aqueous and the OH minus aqueous. So here in this first equation, we can say that Ka can be obtained by concentration of the ammonia times the concentration of the H3O positive ion divided by the concentration of the NH4 positive. While the Kb can be obtained by concentration of the NH4 positive ion times the concentration of OH negative ion divided by the concentration of NH3. So thus, the product of Ka times Kb. What will happen when the Ka times the Kb? So this is what will happen. We can cancel between NH4 plus and NH4 plus, and finally, the only species that remain is concentration of H3O positive and the OH negative. So this species refer to the Kw as we learned previous part. So Ka times Kb equal to Kw, which is referred to value of 1 exponential of negative 14.
Explain qualitatively salt hydrolysis. Using hydrolysis equations. And classify the salts formed from the reaction between 1. Strong acid and strong base. 2. Strong acid and weak base. 3. Weak acid and strong base.
As we learned before during our Form 4 and Form 5 studies, salts form when the acids react with bases. This process we call the neutralization. The salt hydrolyzes in the direction of an anion, which is negative ion, or cation, which is positive ion, of a salt, or both, with water. Here is a general equation of this neutralization concept between acid and base. So the salt form together with water. So if the salt dissociation equation is to be like this, it form the M positive and X minus, is considered as the cation of the salt having a cation hydrolysis in water to form the MOH aqueous and H plus to produce the H plus ion, while the anion of X minus in water, the anion hydrolysis to form the HX aqueous plus the OH minus aqueous. Here, the type of salt that can be determined by the steps below. How we are going to determine either the salt is from the strong acid or strong base, or neutral salt, or basic or acidic salt. So first step you need to do is to write the equation of salt formation. Second step is to write the salt dissociation of equation. The step number 3 followed by the identify the strong conjugate ions and hydrolyze it with water. And finally, determine the type of salt according to the formation of either H plus or OH minus. For neutral salt, the pH of the neutral salt must be 7. Example, sodium chloride. From neutralization reaction of strong acid with strong bases, salts that form is a neutral salts. Here is an example how the sodium chloride form from the strong acid of HCl and strong base of NaOH. In aqueous solution, a neutral salt is about to dissociate completely. So the salt is completely dissociate. As we can see here, the arrow show the completely dissociate to form the Na plus aqueous and the Cl minus aqueous. Both ions do not hydrolyze water molecule. So there is no production of extra H plus ion or either the OH minus ion. Hence that the solution is a neutral. What will happen if you have compound like this, NH4Cl? This NH4Cl having a pH less than 7. It shows that it is an acidic salt. To prove this acidic salt is formed when the strong acid react with weak base. Example, HCl, strong acid react with ammonia, which is weak base. It's going to form the NH4Cl. So this NH4Cl as a salt dissociate completely to form the NH4 positive and the Cl minus. The NH4 positive is a strong conjugate acid because it came from the weak base, while the Cl minus a weak conjugate base because it comes from the strong acid. So NH4 positive as a strong conjugate acid react with a H2O. It's going to form a weak base of NH3 aqueous and H3 positive aqueous. So the NH4 positive is a strong conjugate acid from a weak base of ammonia. it hydrolyzes water molecule by donating a proton or H plus to form the ammonia, and H3O positive thus makes this solution is an acidic salt solution. Now we come to show the basic salt solution. Here is an example of CH3COO and A, sodium acetate solution. In this sodium acetate solution, the pH is rated to be more than 7. It's going to form from the neutralization process of weak acid and a strong bases. For example, an acetic acid of CH3COH aqueous react with a strong base of NaOH aqueous to form a salt of CH3CONA and H2O. Weak acid react with a strong acid and the salt form called as a basic salt. So to prove that this is basic salt, so this aqueous solution of salt dissociate completely to form the ion of CH3CO- aqueous and the Na plus aqueous. Here, if you look, the strong conjugate base is a CH3CO-, while the weak conjugate acid is Na plus. So the equation for this hydrolysis will be, we take the strong one, CH3CO- aqueous, that react with H2O, so it's going to form the weak acid of CH3COH and the OH-. So the acetate ion of CH3COO- is a strong conjugate base from the weak acid, which is CH3COH. So it's hydrolyzed the water molecule by accepting a proton of the H plus to form the CH3COH and the OH-. Thus, the solution become a basic solutions. As a summary for this part of salt, we can conclude that when the strong acid and strong base mix together, the pH of the solution that form is equal to 7, so it's referred to the neutral aqueous solution, which is no hydrolysis can be occur. If the strong acid and weak base mix together, the pH of a solution will become less than 7. That shows that this acidic solution will form as a result. So the type of hydrolysis that occur is cationic hydrolysis. While the weak acid react with a strong base, what happens? The pH will be more than 7. So the aqueous solution that form is a basic solution. So the type of hydrolysis is an ionic hydrolysis solution compound.